Hello students, this is video number 4 of Mechanics of Solid. In this video, we have solved one problem on compound bar, that is bar consists of different material. And also, I have explained to find the deformation of a bar which is gradually tapering bar. That is, one end of the bar is of higher diameter while the other end of the bar is of the lower diameter, and it is uniformly tapered. So for a tapered bar, the deformation has been discussed in this video. Let us see. So this is question number 3 of most simple stress and strain. Total length of a compound bar is 1.5 meter. Area of aluminium is twice that of steel. Load is 200 kilonewton tensile. Elongation of aluminium is equal to that of steel. Take Young's modulus of steel 200 GPa gigapascal and Young's modulus of aluminium is 200 by 3 GPa. Find the length of steel and aluminium. You can imagine a member like this. Suppose this is the portion, aluminium portion, this is steel portion. Such type of members are called compound bar. It consists of two different material. First portion may be aluminium, then steel, or first steel, then aluminium. The length is not given. The total length, of course, is given is 1.5 meter. So let us try to solve it. So given data is length of aluminium plus length of steel is 1.5 meters. Right? Area of aluminium is twice area of steel. Area is not given, only comparative magnitude is given. Area of aluminium is double of area of steel. Young's modulus of aluminium is 200 by 3 GPa, and where steel it is 200 GPa. This GPa is 200 by 3 kilonewton per mm square. This is 200 kilonewton per mm square. Gigapascal is kilonewton per mm square. Now, suppose we find the and one more data is given is change in length of aluminium. DL of aluminium is equal to DL of steel. Elongation of aluminium is equal to that of steel. This is given. These two data is given. So also here load of aluminium will be equal to load of steel because 200 kilonewton is acting throughout from top to bottom. So the steel is under 200 tensile and aluminium will also be under the load of 200 kilonewton tensile. So this is also same. Now this is the same. So let us find one by one. Suppose DL of aluminium will be PL into LL by A aluminium into E aluminium. We know change in length of steel will be PS into LS AS ES. Now according to the question, DLL and DLS are same, so these two will be same. So PL LL area of aluminium, Young's modulus of aluminium should be equal to PS LS AS ES. Now because PL and AS will be same, they cancel each other. Area of steel or area of aluminium is twice of area of steel. So we can write for aluminum steel, we can write twice of steel. So this is twice of age of steel. So age of steel will also cancel. Remaining is LL, LS. So length of aluminium by 2 into 200 by 3 will be equal to length of steel 200. So even 200 will also get cancelled. Finally, what we find is this 3 will go up, 2 will go this side. So 2 of LS is 3 of LL. That means LS is equal to 3 by 2 length of aluminium. Now, because length of aluminium plus length of steel is equal to 1.5 and length of aluminium, length of steel is 3 by 2 of length of aluminium 1.5. So taking length of aluminium common, 1 plus 3 by 2, 1.5 meter. This is length of aluminium, 2 3 5 by 2, 1.5. So length of aluminium will be 1.5 into 2 by 5. It is 0.6 meters. Putting in this first one, or in length of steel is equal to, because we know length of steel now can be found out, length of steel is equal to 3 by 2 of length of aluminium, so it is 0.9 meters. So both length of steel and length of aluminium has been found out. This is one question. Okay. Now we'll go to the other type of problems, like bars of uniformly tapering section. That means the bars are of not uniform section. The section is gradually decreasing or increasing. So how to solve them? We'll see it. So this is bar of uniformly tapering section. This looks like this. One end of the bar is of a larger diameter. The other end of the bar is of the smaller diameter. From D1 to D2, it is tapered gradually. Okay. Now, if such type of load is subjected to pull or push from both the ends of the amount P kilonewton, there will be again deformation, there will be stress, strain, and we will be finding the stress, strain, and the change in length. How to find it, how to deal such a problem, we'll see. So what to do is, we'll consider one thin element between at a distance of x meter from suppose this end. We'll consider one thin element. This thin element is brought out. I have kept it here. This is the thin element taken out from the total, from within the length of the bar. Now the length of this thin element is dx. Total length is dx, very small length. It is again subjected to load P. We'll find the deformation of this element and the change in length of this element. Such type of element are innumerable here. Or if we add the change in length of all such thin elements, then the total deformation can be found out. So considering the thin element whose length is dx, which is subject to load, whose diameter is not d2, not d1, its diameter will be d dash, something less than d1 and more than d2. So let us first find what is the d dash. D dash will be more than d2 but less than d1. So d2 plus something, d2 plus change in between d1 d2 in the whole length multiplied with the distance from d to x. This, if d2 is added with this vector, the d dash can be found out. So d dash, which is the diameter of the section or thin element, is d2 plus this much. Now this term d1 minus d2 by L, for convenience, I will replace it with one letter K, because all these three things are constant. D1, D2, L, all are constant things. So I change with the constant K. So the expression will be easy looking. D dash is equal to D2 plus Kx, where K is equal to D1 minus D2 by L. Now, I will attempt to find the change in length of this thin element. As usual, change in length of this element will be in the formula PL by AE. See, P is P, L is the length of the member, dx is the length, load is P, original length is PL, so PL by area, area from D dash, so pi by 4 D dash the square into Young's modulus, PL by AE. As usual, I have written the formula P, and this 4 will go to the top. It becomes 4P dx pi E D dash square. D dash square, not D1, D dash square. Okay. Now this D dash square is equal to D2 plus Kx the whole square. So this is the change in length of this thin element. Okay. Now if we integrate this change in length for all such elements, the total elongation can be found out. So the total elongation is dl is integration of such change in length of smaller elements. Innumerable small elements will change like this, and such changes, if added together, will give you the total changes. So dl is integration of dlx. So now dlx has been got an expression like this, 4p dx. So this will be integrated. If you integrate this from, of course, from 0 to L, we have to consider all such elements from x0 to xl. Within x0 to xl, there are many elements, those has to be integrated. So the limit will be x from 0 to x from L. So now integration within limit 0 to L, 4p dx pi E. This is power 2 square is taken to the numerator, it will be minus 2. Now integrating this, 4p pi is constant. Integration of this is 1 by d2 kx power minus 1, so it has come down, k out, limit is 0 to L. Try to understand this. If you have any doubt, you can ask me in comment. So this is 4p pi E, k is taken out now again. Remaining is this only. For this we have to put limit. If you put limit, if you put L, KL, so KL will be only D1 minus D2. So D2, while putting KL, it will be D2 plus KX times D1 minus D2. Again putting the limit 0 here, this will be 0. So D2 plus 0. Okay. Now 4p pi EK, it is 1 by 2, 1 by D2 positive, negative is 1 by D1. So 1 by D2 minus 1 by D1. So D1 D2, D1 minus D2 by D1 D2. This one. Again there is a K here. We know K is equal to D1 minus D2 by L. So K means it will be D1 minus D2. So D1 minus D2 will get cancelled. That L, D1 minus D2 by L, L will go up. So 4PL pi E, it has been cancelled. Remaining is D1 D2. So this is the answer. Total elongation is 4PL pi E D1 D2. Mind it, D1 D2 are the diameters at the ends of the bar, bigger and smaller, extreme ends, so diameter. P is the load, L is length. That's all. So we can find the change in length of even of a tapered bar whose diameter is not constant. It is gradually tapered. For this you can use this formula. You can remember this formula, 4PL by pi E D1 D2. Okay.